In this presentation, I'm going to introduce our work on semantic segmentation for driving scenes. This is a joint work with my colleagues, Karan, Fitzham, Kevin, Andrew, Brian at NVIDIA Research, and my advisor Sean. In standard semantic segmentation pipelines, we use manually annotated image label pairs as input and train a deep neural network to learn the mapping between them. However, it is very expensive to collect a large dataset due to the per-pixel annotation process. For example, annotating a 1K by 2K image in Cityscape dataset takes about 90 minutes. Due to the expensive annotation process, most benchmark datasets now only have limited number of image label pairs, which is orders of magnitude smaller than other datasets in other computer vision domain. But we notice that for autonomous driving, we usually have access to unlimited video recordings as the car drives around. We just don't have enough ground truth. The data is labeled only sparsely. So we wonder, can we use adjacent unlabeled video frames to help improve the performance of semantic segmentation? There is a previous approach to do this, called label propagation. The idea is to first learn a transformation function given video frames, such as optical flow, and then use a function to propagate semantic labels to adjacent frames. This method has several limitations, like problems resulting from occlusion and misalignment. In this work, we propose a data synthesis method based on video prediction to create more training samples. We explore the video prediction model's ability to predict future frames in order to also predict future labels. The video prediction network can be trained in a self-supervised way to learn how objects move between frames. This can effectively handle the occlusion problem. In addition, we observe that for traditional label propagation, there is often a misalignment between the ground truth video frames and the propagate labels due to inaccurate motion estimation. We show two examples here, the distorted street poles and the distorted human legs in the propagate labels. In order to obtain more accurately aligned image label pairs, we propose joint propagation. Instead of using ground truth video frames, we use propagated frames. Although the propagated frames might not look realistic as the ground truth frames, they match perfectly with the propagate labels. This simple strategy is important to learn accurate model since semantic segmentation is a dense per-pixel estimation problem. Using our approach, we can scale up the training set in an autoregressive manner by propagating over more and more time steps. Here, we show some propagated training samples. We predict from 5 past frames to 5 future frames. Only the middle one has a ground truth label, while the others are all predicted. If you look at the rightmost column, we can see how the method can generate useful data for us. However, synthesized data often has artifacts. We observe that our model has high uncertainty around class boundaries. We therefore propose a modification to the class label space that allows us to predict multiple classes at boundary pixels. Simply speaking, we de-emphasize the learning of border pixels from the augmented data. This technique helps our training process be robust to label noise. For results, first, we compare our video prediction model and FlowNet2. Visually, we can see that the video prediction network can handle occlusion much better than FlowNet2. And quantitatively, the video prediction network also outperforms FlowNet2 at all propagation lengths. Next, we show the effectiveness of label relaxation. With label relaxation performs much better than without it at all propagation lengths. We can now benefit from longer range training data propagation. For single image segmentation tasks without using our augmented data, label relaxation can also handle ambiguous labeling problems, which leads to a significant performance improvement. We also show some video samples to demonstrate the advantage of our proposed method. We can see that a bicycle is segmented from the pedestrians correctly. The signs are segmented as a whole, and the fences can be distinguished from walls. Quantitatively, we achieve state-of-the-art results on 3 benchmark datasets, Cityscape, CamVid, and KITTI. To conclude, we propose a semi-supervised learning pipeline to utilize unlabeled video frames to improve segmentation performance. I want to point out that our techniques are general. You can use pre-trained video prediction models to augment your dataset regardless of whether you have video data or not. You can use joint image label propagation to handle misalignment in other vision tasks. You may also use boundary label relaxation for any dense per pixel estimation problem to address label noise. For more information, please check our project webpage and our released code at NVIDIA/Semantic Segmentation. Thank you.